Hello and welcome back to our second lecture on the foundations of machine learning as it relates to data science. In this lecture, we will proceed by building on what we have already seen and work with the PAC model of learning and apply it to the context that we've been building up to do a provably correct way of learning. But correctness here is something we will describe in a second, Boolean functions. So our prototypical objects that we are trying to learn are Boolean functions. And we have, if you remember, notions such as the quality and the confidence associated with the PAC model. And we'll now start quantifying those. But above all, we'll end up proving the theorem that we set out to do in the previous lecture, the first lecture on machine learning. So to do that, we'll start out with a quick recapitulation of the model, but also a couple of useful additional definitions that we'll add to our repertoire of things we have already seen and use them collectively to actually go through our proof. And then in the second segment of this lecture, work out the proof. So what's the background that we did? Well, we started out by talking about the PAC model, and this model had, if you look back at what we did, two key elements in it. One was a notion of quality captured through the parameter epsilon, and the other was a confidence with which you are able to assert that you are learning with that quality captured through the parameter delta. There was also a third element that was central to this, and that had to do with this all-knowing oracle that would provide us, in some fashion that we didn't describe, examples of the function we are trying to learn. And of course, the first thing I want to observe is the more you have to look at examples, the more it costs. But of course, you would like to, with very few examples, ideally the least number for a given function, be able to learn with high probability and find the hypothesis which best matches, subject to the epsilon bound, the quality consideration, the concept, which is the Boolean function we are trying to learn. So that's the tension. We want to learn with low cost, but at the same time, we want to be able to guarantee that our quality is high, that our confidence is high. So the main template for today's discussion is to focus on a very concrete form of this goal, the theorem that we described and gave you informal intuition about in the previous lecture. So we're building up to that today. So we'll start out by giving a formal proof of the theorem, but then we will end this lecture, which is the second lecture and the final lecture on the foundations of machine learning, by talking about what it means to learn functions beyond Boolean functions, functions in general. And also, to illustrate that point, give a concrete, helpful example of our framework in action. First useful thing to redefine in a slightly different way is the concept of the inner product of two functions. So you're given Boolean functions for our purposes, f and g, which map -1 and +1, let's say, into the real numbers. Then we define the inner product fg to be simply as we range over different values of x, f of x times g of x summed over all possible values times 1 over 2 to the n, where you have 2 to the n possible values, since the inputs are n vectors, or these are n-dimensional inputs. So since f and g are both now well-defined functions, you can potentially compute this in a product. I want to quickly mention this in passing because I think it's a fairly straightforward thing to conclude, that down here below, you see also another way of writing exactly the same expression, and that is to think about taking fx times gx, but taking its expectation, which is nothing but all the values divided by 2 to the n, provided this notation here, just to remind ourselves in this lecture, means you're drawing the inputs uniformly at random from the set of all possible inputs, the 2 to the n inputs. So those are essentially different ways of looking at that. It's sometimes convenient to look at the second form of this expression, which I have indicated here, since we'll refer back to it in a few minutes, by this asterisk symbol. So when I say expression that was marked with an asterisk, we mean this particular form of the inner product written as an expectation. So one useful classical fact, simple but very useful fact, is given such Boolean functions, but now let's consider the case we've always been looking at, functions that map their inputs not into any real number, but just into the values -1 and +1. And we also remember that we could write out such a function, and we've seen this several times, as the sum of its Fourier coefficients. So without repeating the particular representation of a Fourier series for a function, I want to claim a well-known fact about the Fourier coefficients, which in this context may be somewhat counterintuitive in the beginning. And so I will actually give a slight explanation for how to conclude that. This is called Parseval's theorem, and it simply says that the sum of all the Fourier coefficients as you range over all the sets from indices 1 through n, the set of all possible values for S, is actually 1. It's at one level a straightforward thing if you have seen these sorts of derivations before, but since this may be new to some of us, I will at least sketch out the argument on how one would approach concluding that this is true. So the first observation I want to make is that Parseval's theorem tells us that Fourier coefficients cannot be arbitrary. They have to obey some nice properties. Most nice of them all is the fact that they add up to 1, which is actually very useful. So from our previous star expression or asterisk expression, we know that a product of f and g can be written in this form of an expectation. So now let's do a simple substitution. Let's throw out g, but replace it with f. So it's the inner product of f with itself. So you would simply think of it as angle brackets f comma f, which is the expectation, and we repeat now f twice. But that's nothing but f x squared, right? Very simple. So now notice the following interesting idea, that since fx is always mapped into either -1 or +1, the square of it is always +1. And so what we have easily concluded, if you look over all possible inputs, is it's really 1 over 2 to the n of 1 added 2 to the n times, and therefore it's 1. So that's sort of one way of concluding that. Okay, so what we have shown is this form, this expectation, equal to 1. But now we will also have to show, to completely derive what we want, is that the inner product of f with itself is also looking to be this expression here. That means the inner product in the first instance is 1, the inner product in the second attempt is this expression, and therefore this expression is 1. To do that, it will both be potentially given as an exercise for us to work through, but it takes a little bit of calculation, nothing very deep, but just mechanical calculation. We refer you to the book that we have sent out an email to all of you as a way of accessing this for this lecture. It's the source material for what we are lecturing today, as credited on the first slide. It's the book by Professor Ryan O'Donnell on the analysis of Boolean functions, and in particular, the latest version of this book on pages 8 and 9, immediately after proposition 1.8 in chapter 1, gives you a way of completing this calculation, and we would encourage you to look at that. And just to remind you again, in case you need a second pointer, if you go to the URL that's listed here and apply for it, they give you free access to the book. It's a straightforward process. So that's one item we will just remember, Parseval's theorem, which is useful as we move forward in proving our main theorem. Second idea is we also define something called an epsilon concentration, which means some of the Fourier coefficients had more weight than others, loosely speaking. We will use a slightly different notational approach and terminology to define the same concept now, because it's more convenient to think about it the way we are about to define. So let's say that given a set S, the Fourier weight, a term we are introducing, okay, of f on this set S is simply f hat S square. That's just a definition. Slightly different way of looking at properties of this set. So the spectral sample of a set S, given function f of course, is the probability distribution in a way that I will just mention, okay, of all possible subsets of the form S drawn from 1 to n. And what do we mean by that? Any given S, we call f hat S square as its probability, P sub S. Okay? Now, is this a real probability? It's a valid probability since first f hat S square is a positive number and it sums to 1 from Parseval's theorem. So that's a way of thinking about it as a probability, correct? So now we had also, and I'll restate this using explicit terminology now, but perhaps in the future I may omit to say this, script f, which you can easily see, is a collection of these sets S. Not all of them, some of them. And we hope that those sets S that are members of script f are the dominant ones. If you remember, this was used to define epsilon concentration in a different way earlier on. So if you now think about the Fourier spectrum of Boolean function f, and epsilon concentrated on f now means it's the sum over all the elements, and we use this slightly counterintuitive notation because it's technically convenient. It's the sum of all those elements S which are not in f. Everybody else is less than equal to a small quantity epsilon, which means you are the big quantity. So when you want to talk about f, you sum those elements that are not in f. And that's what it says here. But now you just sum over P sub S instead of f hat square. So this is simply a nice way of thinking about it. It is that the probability of the coefficients associated with subsets f from f through those which are not in f. So it's a different way of thinking about the dominant set where all the weight is concentrated. So with this, we will now build up towards actually proving the theorem that we had stated earlier on about how we can learn through the PAC model Boolean functions effectively.